everyone. Welcome to Let's Code Physics. Today is the first day in a new series about modeling electron behavior in a circuit. So we often think of circuits as these sometimes quite literal black boxes where we don't know what's going on inside. We know that there are electrons moving around inside, but it sometimes is difficult to visualize how the physical motion of the electron leads to the behavior of the circuit. So starting in this episode, we're going to build a simulation of electrons physically going around a circuit and examine how their physical behavior makes happen the goings on of the circuits, making light bulbs light up and capacitors charge, and maybe we can even work out an inductor creating a magnetic field. But first, I wanted to talk about something that bothered me for a long time as a physics major. I've written up here the central equation for a Physics 1 class, F equals ma, good old Newton's second law, the constant mass version. And then over here, the central equation for a Physics 2 class dealing with circuits, V equals IR, Ohm's law. These two are very similar to each other, in that they've got a thing on the left-hand side that is causing motion in a very generic sense. They've got a thing on the right-hand side that resists motion, in this case mass, in this case resistance. And they've got a variable describing the motion of stuff, in this case the acceleration, in this case the current. But I want to take a minute today to talk about why this has always bothered me. Because if you take this equation and apply it to electrons, so the way you would move an electron is have your force be an electric field times the electron's charge. So this is the strength of the electric field that you turn on. This is the charge of the electron, a constant of the universe. It seems like every electron has the same E, we're pretty sure. That should equal mass times the acceleration. Now, I can't really measure the acceleration of an electron, but if I think about it, when I have an electron going by at a certain velocity, then I can relate that velocity to the current going through, right? This nice current here. The way I can think about that is that velocity is distance over time, current is charge over time. Actually, let's make that a E. There we go. I can think of this as the electron charge going over time. So I can think of these two as being related if I just think about, say, for example, how much distance the electron travels, from one point in time to the next. I can convert this thing into this thing pretty easily. What that means is that this thing should be proportional to the maybe some numbers times the rate of change of current, because the velocity and the current are going to be proportional to each other. Acceleration is the rate of change of velocity, so this thing should be proportional to the rate of change of the current. And I said somewhere in here was going to be a length, so maybe we can divide that out to either side, so maybe we can get the electric field per unit length. So you would need more power to create a stronger electric field over a longer length, for example. Well, if you come over here to Ohm's law, you get something a bit different, because this V, this electric potential, this is in fact the electric field divided by length, more or less. It's really the derivative of E over L, derivative of E with respect to L, but the point is it's electric field per unit length, equals the resistance, so something involving the how tightly packed the material is, so that you can think of that as kind of like a mass for the thing, a resistance and inertia. So you get some, actually let's flip that around. You get that over here, what you're left with is the current. And so over here, according to Newton, the electric field should produce a change in current. It should produce an increase in current. But according to Ohm, an electric field produces a single solid current, a uniform, constant current. Those two equations, it doesn't seem like they can be reconciled. And for a long time, I was not really sure how to reconcile those. A long time meaning a couple of years while I was an undergrad. I should have opened up another one of these. Brian, you need to cut back that previous part there. Okay. No, you go away. You stay there. Well, it turns out the way you reconcile these two is by considering that this is not the only force acting on the system. Because what you have, let's draw a friendly electron here. So your electron is being pulled along by the electric field. So it's got a velocity that is increasing as it goes this way. Let's say the electric field's pointing this way. So your electron is going to go from having a velocity like this to having a velocity like this to having a velocity like this. It's going to be getting faster as it moves along in the direction as the electric field pulls it along. But what you also have to take into consideration is all the stuff that it can collide with, because this material is made of atoms. And so you've got these atoms that are here. We'll call it A for atom. Maybe it's copper, maybe it's iron, who knows. When the electron hits the atom, it's going to recoil away. Now, that's not a constant force on it. It's a roughly zero force until it gets really, really close, at which point it has the collision. There's a little bit of Coulomb force going on in here because at first it's attracted by any residual positive charge on the atom, but then it gets repelled, because it's hitting this hard sphere here. And basically what that does is it causes a reset to the electron's velocity. So let's say the electron's velocity had a certain speed here. It's going to recoil off in a randomized direction and basically reset its speed. At that point, the electric field acts on it again, and so now the electron is going to continue, and it's going to accelerate in this direction until, again, it hits yet another atom over here, and then it's got to recoil off in another direction, again resetting its speed. And what I had not accounted for in my naive understanding, or my initial understanding, I shouldn't say naive, in my initial understanding was that this speed basically resets every time and the direction gets randomized. And what that means is that this acceleration is not steady. It keeps resetting every now and then. The analogy to think of is that you imagine that you're in a car. Here's another one of my lovely Goomba cars. Your car, you press the accelerator, is going to get faster as you move along until you reach a stop sign. I think that's 8 sides. Oh, that is a crumpled stop sign. I'm so sorry. I've got Goomba and I've got Mario over here. So sorry. Here's a stop sign. And of course, at that point, the car has to come to a stop. At least it's supposed to come to a stop. And that means that its speed has to start over again. And so even though you're applying, my car is now crossing paths with my electron, drawing not to scale. And so what that means is that even though you're applying the accelerator, you're having to also apply the brake. And so your speed is roughly constant even though you're always accelerating. Well, that's the same thing that's happening here between these atoms. And so the way we model that is that we assume that there's an average time called the scattering time between collisions. This thing is sometimes given the symbol tau in a textbook. Boy, that is an ugly tau. I can do better than that. We call this the average scattering time, meaning the electron goes some average time tau between collisions. You could also convert that into a scattering length. We're going to use it as a scattering time today. So what I want us to model today is this behavior of this electron that gets accelerated in a certain direction. So there's this consistent electric field pulling it in this one consistent direction, but then the electron will randomly run into atoms, with a probability that's scaled based on this tau. So here's the code that I've got worked up. We'll talk about what this graph does in a second. The first thing I've done is I've defined an electron. In my chemistry textbooks, electrons are always green, so I always envision electrons as green particles. I know they don't actually have a color, but that just helps 10th grade me remember which particle I'm dealing with. We're going to start it over on the left-hand side of the screen. We are giving it a relatively small size compared to the size of the screen. We're going to say that its default speed, the speed that it resets to every time, is 1. So that'll be sort of its base speed, if you will. And then we're going to turn on an electric field. So the electric field needs to be a vector. Really, this is the field times the charge divided by the mass. So we're just wrapping all those up into one quantity here. Because if you make the charge stronger, then the effect of the field is stronger. If you make the mass heavier, the effect of the field is weaker. But then that all gets lumped together here. So we're not going to worry about the rest of them. Let's see, we're going to worry about them individually. So we're giving that a value of 0.5, and then we're giving our electron an initial velocity slightly to the right. I could make that 0 if I wanted to. We can play around with that later. And then we're defining our electron scattering time, and I've recently gotten more heavily into object-oriented programming, so I'm now comfortable with just tacking on dot something onto here. So now this electron gets to inherit each of these things so that we can keep track of them. In a future episode, when we have multiple electrons, I'll make a class called electron where we associate all these values to each of those electrons. And so this is the scattering time. This is the average amount of time that our electron will go between collisions. It doesn't mean that every 0.1 seconds it'll have a collision. It means on average every 0.1 seconds it'll have a collision. So the way we're going to implement that is we are doing our while loop here. We've got our Euler-Kromer method set up. We are randomly determining whether the electron gets scattered in these two lines here. So we're picking a number between 0 and 1, and then we are determining whether that number is less than this factor here. So this is the electron scattering time is in the denominator, because the longer the average scattering time, the less likely it should be for a collision. So you can think of this roughly as giving you the spacing between atoms. So if the atoms are widely spaced apart, then there's a very low probability of having a scattering event. If the atoms are very close together, then you're dividing by a smaller number, and there's a very high probability of getting a scattering event. And we're taking dt and dividing it by that so that if we adjust our time step, our probabilities don't suddenly change. Also, that way it has units of probability because it's a time divided by a time, so that gives us a pure number. And so we're now turning scattered from a float into a Boolean. Python doesn't seem to mind that. So we're checking whether scattered is less than this. Actually, that might be a little bit clearer if I do it like that. There we go. So we're checking this Boolean condition here, setting that equal to scattered here, or recording it under scattered there. So if we have a scattering event, meaning if the random number distribution selected, between 0 and this fraction, then we need to scatter the thing. So we need a randomized angle. So remember, once you have a scattering event, once you have a collision, we need a randomized angle for the electron to pop out at. And this can be any angle, because obviously if it hits this side of if it hits, around here on the atom, it's going to tend to reflect back this way. If it grazes the top of the atom, though, it might glance off this way. If it grazes the bottom of the atom, it might glance off this way. So we can get just about any angle between 0 to 180 or 0 to negative 180. Which amounts to 0 to 2 pi in Python speak. Now notice we're not actually creating the atoms here, because we want this to be randomized. We want this to be a random event, so that we can control the scattering time directly, because we're going to revisit this later when we start looking at the material's resistivity, big word for later. So if that's the case, then what we do is we reset the electron's velocity. We give it its basic speed, this electron speed that we had up here, and we're shooting it off at this vector. So in other words, we're not doing anything with the electric field in the event of getting scattered. The electric field doesn't have any impact. We update the velocity like this. Otherwise, if it's not being scattered, which should be most of the time, right, because our scattering time is 0.1, our dt is 0.01, so we're taking 0.01 divided by 0.1, so that's the same thing as 0.01 times 10, so this is a 1 in 10 chance of having a scattering event. So 1 out of every 10 times we should get a scattering event, but 9 out of every 10 frame increments we should get just normal acceleration behavior. Our velocity gets updated by the electric field times dt. I am fully committing myself now to the plus equals notation that is so convenient in Python. then we update the electron's position. Notice we're going to update the position the same way regardless of whether we had a scattering event, because either way we've updated the velocity. We update the position now in the same way. We just add on the velocity times the time step. And then I want to keep track of the electron's average position in the x direction. I'm just going to be interested in the x direction. That's the left and right direction for right now, just because that's the direction of our electric field, is in the x direction. It doesn't have a y component or z component. So the y and z should average out. In fact, since my initial velocity doesn't have a y component, and since I'm not scattering in the z direction, I shouldn't have any motion in and out of the screen. And we'll use this ruler later to confirm that. So what I should get if I run this is an electron that most of the time is accelerating forward, and 1 out of every 10 frames should get scattered at a randomized angle. So let's see what that does. Okay, here's our electron. You notice, kind of like we talked about, its up and down is randomized. You notice it seems like it's coming at you like it did just now. That's a result of the zoom factor of this display. That's not it actually moving into or out of the screen. We'll put a reference bar on a little bit later to get that. But you notice that in terms of up and down, it's more or less averaging out to 0, right? So it's a little bit below the middle of the screen now, and a little up above the screen and a little bit. What's interesting about that is that we're accelerating it in the x direction, which means it should be moving pretty steadily in the x direction. Now we're not seeing that too well here. Basically it's being scattered significantly more than it is being accelerated. So right now we're sort of averaging everything out in terms of x. Oh, except it just now pushed forward in the x a bit. So we went a few frames without having a whole lot of scattering events. So it was able to push forward in the x right here. So now you notice it's a bit farther over to the right. It's also smaller, again, because of that zoom factor. But now it seems to be hovering around here, kind of like it hovered around 0 down here. Oh, it got another push to the right. And so what we'll see as this runs is that it's going to keep getting pushed farther to the right, which means farther up on this graph, farther to the right on this animation. Again, because of that electric field. Oh, now it dipped back down. Yeah, so the electric field continues to push it to the right. The randomized scattering events are pushing it in any direction, basically. Let's make that a little bit easier to view. I put on this ruler here. It's not marked or anything. It's just a box of length 1. It'll be centered on the screen, a little bit low. We can use that to get an idea of how far the electron moves on the animation. So let's run this with the ruler. Okay, so you get an idea now of where the electron is. So this thing has a width of 1. So you get an idea now of how the thing is zooming out. And of course, the behavior is randomized, so we won't get the same results that we got last time. Again, we get hovering around, and then we get a push in that direction. Basically there, we're getting a couple of helpful scattering events that allow it to, kind of move along. But basically, if I can zoom in on here, right? Yeah, basically if you zoom in on this, it's a bunch of, connected straight lines, basically, because it's being scattered and accelerated. Now this is getting a pretty steady trend. So if you were to take the average of this thing, it's got a pretty consistent slope, right? So if your position versus time graph has a pretty consistent slope, then that means it's got more or less a constant velocity, right? It's oscillating around that, but it's oscillating around a more or less straight line. It's not going quadratic like you would expect from the Newton's second law model. It's going in a straight line, like you would expect from the Ohm's law, V equals IR, since the velocity is basically an indication of the current. This is telling me that it's got basically a constant current system. If I wanted to, well, we'll do this in a future episode, we'll put a whole bunch of electrons in there, and then we can get their average velocity, and that'll come out to be pretty consistent. But you can get an idea here that this velocity is pretty consistent. Speaking of which, let's do a little bit of an experiment. So this thing has gone 400 units in the x direction in about 15 seconds. Or 520. So let's do a little bit of math here. Calculator, where are you? There we go. So we've got about 520... Oops, excuse me, other way around. We've gone 20 in 500 seconds. So right now it's got a speed of 0.04. Now according to Ohm's law, let's go back over to Ohm's law, the current should be proportional to that electric field. So if I double the electric field, I should be able to get double my velocity. So I should be able to get 0.08 if I double my electric field. So let's change this from a 0.5 to a 1. So going from 1/2 to 1, that's doubling. Okay, this thing is definitely jostling about more significantly. We have not changed the scattering time. The scattering time is what goes into the resistance of the object, or of the material, and so we've got the same resistance. We've just got a higher electric field now, and so we're looking to see whether we get a speed of about 0.08. Let's see, we got out to, how did we get that last, how long did we let that go last time? We let that go until about 500 there, okay. Okay, we reached 20 in about 250 at this point, just roughly, which should be double that, right? So 20 divided by 250 gives us a 0.08. So we doubled our electric field and we doubled our speed. So that, the scattering, is what's giving us this constant velocity. If we didn't have the scattering time, or if I made the scattering time really, really large, then we wouldn't have any scattering. We would just have the electric field acting on it. So if I made this incredibly big, right, that basically makes this probability 0. Then we would get accelerated movements. You notice there we get our parabola, like you'd expect from Newton's second law. So there's Newton's second law. So it's the scattering that gives you the V equals IR, the constant velocity or constant current motion. So that's pretty cool. So this has been neat for me to do, to be able to visualize this thing I didn't understand as an undergraduate. I hope that's a helpful visualization to folks out there that may be struggling with Ohm's law and where it comes from and how to rationalize physics 2 with physics 1. But that's basically how you do it. It's this scattering time. Let's do one more thing. Let's see what happens if we change our scattering time. So right now we've got a 0.08 speed. Let's see what happens if we double our scattering time. So we're going from 0.1 to 0.2. So scattering will happen twice as often now. And what I want to see is what that does to the speed. Is that going to cut it in half, or is that going to do something more nuanced with it, like cut it by a fourth or square root of 2 or something like that? So we'll let this go out for a little bit like we did before. We got it out to about 20 last time. Let's see. Okay, we reached 20 in about 100 and... Oops. See, we reached 20 in about 130 seconds. So if I take 20 divided by 130, I've got a 0.15. Wait a minute, that doesn't seem right. That makes it faster. Am I taking the right thing there? Alright, let's try that again. Let's try... Oh, no. Alright, let's try 40 divided by 20. There we go. I think I put in the wrong number. 40 divided by 200 is 0.2. Why is it going faster with a hot... Oh, excuse me. It should be going faster because I'm sorry. Gosh, I hate putting things in denominators. We made the scattering time larger, and that made our speed faster. Yes, that is exactly what you would expect because we're making the scattering less probable because we have... because we've increased the denominator here. Oops, my mouth went one way, my brain went the other. But what you notice, we've gone from 0.08 to 0.2. That's a little bit more than double. I mean, this is about 0.1 to 0.2, so I don't know that that's different enough to call that to call that significantly different than doubling. Let's try cutting the scattering time in half. Okay, now we're making the stuff denser, so that should slow down our speed. Oh, and I wasn't taking into account the fact that we started at -1, so I did not do a very good job taking the slope there. Oh well, we still got the general idea. You know, it's an error of 1 out of 20, which is not that bad. Here, I think it's pretty safe to say this thing is moving a bit more slowly because we're at about 200 now. Or excuse me, we're at 150 now. We're only at 7.5. So let's see what happens when we get out to 200. I mean, this thing is staying flat now. Yeah, so at 200, we haven't even broken past 10 yet. So if I calculate the speed there, let's say we've gone 10, just because I need to take into account that -1 down there. So let's say we went 10 in 200. That takes us down to 0.05. So it's not quite a linear relationship. Of course, I also don't have a whole lot of data points. It'll be better to take that when we've got a whole lot of electrons running through the material. But anyway, that is a fun way to look at where Ohm's law comes from. Would love to see you download the code. It's in the description below. If you'd like to play around with the scattering time and the electric field, if you get something else interesting, or if you get some different speed behavior than this, would love to see that in the comments below. Or you can tweet us at LetsCodePhysics. Thank you so much for watching. I will see you next time. Bye-bye.